Hi, my name is Brad Pfeiffer. I'm an undergraduate student at Oakland University in the Electrical Engineering Department. I've been working with Assistant Professor Dr. R. Fifar on this topic throughout the summer. The topic is EV penetration for minimizing power system upgrades, which is essentially how can we use electric vehicles to support the grid. The idea begins with the assumption that electric vehicles could discharge to the grid in order for support during the daytime while the cars charge at night. On average, cars sit 22 hours a day, so this leads for a tremendous opportunity for electric vehicles to be used as a cloud battery network, if you will. During peak hours, battery energy will be discharged and the peak may be softened instead of the power system buying an additional generator for that load. By simple math, an electric vehicle could theoretically power a home for 3 days, some of the larger batteries. So that gives you a sense of scale of the batteries. The test system we use is a PG&E 69 bus power flow model. We have chosen 10 different EVs for a realistic sense of population density based on their sales numbers. So a power flow is ran half hourly for a whole day. There is a load coefficient that allows us to make a load curve during the day and then adjust it based on electric vehicle discharge distributed probabilistically. Here are some of the results that we've found so far. Hopefully the results plots are not too small for you to see. Starting on the top left corner, there is what would be the minimal result, so some peak shaving during the second half of the load curve and some valley filling in the beginning. And then the maximum result is with a 70% population of electric vehicles participating and a depth of discharge at 50% for their battery. There is a very large peak shaving occurrence, and as well as a very large valley filling during the nighttime. In the middle, we can see the peak shaving by participation. So at 100 electric vehicles participating, we could shave 6% of our system's peak. And that number is less with a different discharge floor. The discharge floor is essentially the lowest percentage that the system would discharge a battery to. So if that number is higher, then there are less results, but that may leave more flexibility for the user. The next plot down shows the aggregated vehicle energy, so the total energy of all of the cars that is available, again by two different levels of discharge floor for flexibility of the user's sake. And then on the right, we have started with a cost index, which shows if we were to pay users dollar per kilowatt hour supplied, how does it compare to a traditional distributed generation system? And we have 3 different lifespans there, so there are 3 different equivalent price points. And so then you would be able to tell, depending on how long the lifespan, where the electric vehicle system would be cheaper to operate. We have concluded that a significant amount of energy is available to be harnessed. Like I said before with the scale, just a couple electric vehicles would provide a large impact on the power system. This impact may improve the reliability and the security of the grid if it was used as a cloud battery backup. There may be less blackouts. Depending on the battery lifespan for the vehicles and the cost at which users will agree to participate, then the system could be cheaper and cleaner than traditional methods. Startup time for generators could be on the order of minutes, while the vehicle-to-grid system could start in a matter of seconds, again with the reliability point. In other works, it's been shown that EV batteries may be useful for not just active power, but reactive power compensation and frequency regulation support. This may be something we look into in the future. And also a survey may be done regarding the price point that users are willing to participate. Because the users do have to be willing to participate in order for everything to work. They have to sacrifice some flexibility in their daily life, their car's operation. Current future work on this project is developing an algorithm to locate the most efficient buses for aggregate discharge stations. Thank you for the opportunity. Have a nice day.